Fine, all right, sorry about that. So every time there's a different connector, and for some reason, one buys the expensive adapter for the Mac, and for some reason it doesn't like something. All right, so last time we stopped discussing this multiple reflection point of view for analyzing this system of a terminated transmission line, and we basically arrived by summing an infinite series, arrived at the same result of how one can transform an impedance RL to the load using a section of a quarter wave transmission line of characteristic impedance. So we also looked at what happens when the boundary conditions are different, the idea of an impedance inverter versus not doing anything. We have a lambda by 2 resonator. We also discussed that even though this response is periodic at specific operating frequencies, again, all of these things, transformations are defined for an ideal operating point. And we discussed the notion of what the bandwidth of such a system might be in terms of how the response starts to deviate from the ideal behavior we wanted as we went away from the frequency. So even though the response is periodic at that exact operating points as you go to higher frequencies, multiples of the length, you saw that the response changes a lot faster than the lowest mode you can actually use. So that so it basically emphasizes the fact that going to the longer length doesn't always benefit. So there are situations where one can actually use that, and there's actually an example from certain research from our group from a few years back. Maybe show that example at the next. So I want to finish up this basic discussion of how when we think about waves propagating on a line today, and then introduce you to some of the standard transmission lines we use in practice, what they are. And then in the next lecture, we will go into a little bit more detail in the physics of those structures in terms of the Maxwell's equations, simplify them for the particular case, and then we see how one can extract the relevant quantities, which is basically the inductance per unit length and the capacitance per unit length, given the geometry and the properties of that structure. So I'm not going to talk too much about this topic. You can read this in Bozar, but just to basically orient you. This is now talking about the most general case, even though in practice, depending on how you look at it, if you say that nothing is ideal, then this is the most general condition you're going to have, because you cannot design characteristic impedance to be exactly 50.0000, so depending on how many decimals you want. Similarly, a load impedance and the source impedance may not be exactly equal to each other. So in that sense, this is the most general picture, but for all practical purposes, this is sort of an artificial picture which you rarely have where these variations are going to be large, unless you have designed an experiment or your experiment has a constraint where you cannot get around. So this is the situation where the load impedance on this side, the section of transmission line in the middle, and the source you have chosen, they all have different impedances. So load impedance is different from the characteristic impedance of the line and the source impedance of the generator. So in that case, you can imagine that there are going to be reflections at both of these boundaries, right? This is where the mismatch occurs. And you can think of this in various ways. If you're interested in seeing how much power is going from the generator, then you could take this part of the circuit use the analysis from last time to transform C of L into a new impedance, which is going to be the impedance seen at this point, so labeled as C, and then treat that as the new load, right? So your new diagram will look like VG, ZG, and then you have Z. Right? This Z in is what you just computed from this section. You can also go the other way because that side is the source. Usually don't do it the other way, but you could in fact compute from this point of view. How does the source impedance look like? But you now have to transform the voltage as well. So it becomes a little bit more complicated if you want to take that. But they are sort of equal. So the discussion in this section talks about a few of these cases where maybe these two are equal, Z0 and ZL are equal, or Zin and Z are equal. So that will remove the reflections from one of the locations, and you will be able to calculate it with a lot more simpler. The most standard situation is going to be that your source impedance and the transmission line you're using are both the same. Then load is dependent on your experiments, you can compute what that happens. So whenever you have a section of transmission line whose characteristic impedance is same as the source impedance, then in some sense nothing actually happens. Okay, so let me just expand on this. You can, for all practical purposes, just ignore the transmission line which is present here, because its only job is to take the signal at this point and then reproduce it at this end. Now, this is of course the most ideal case, lossless transmission line perfectly matched to the source impedance. Because you know that there will be no reflections here, so you will set up the waves, the forward going wave only in this case, and that will just propagate and arrive at this end. The only change it's going to experience in that is a phase shift. Right, an overall phase shift, which depends on the speed of propagation of microwaves in this transmission line and the effective. But an overall phase of this type has no significance on how it's going to interact with the load. So you can just completely ignore for all practical purposes that overall phase. This is not true if the impedances are different, so then have both reflected and transmitted. Same thing applies when you look at it from the other side. If your Z of L and Z of naught are the same. So again, when we talk about things being the same, most cases where, and I guess almost for all practical purposes, these are all real characteristic impedance and real load effects. Transmission lines with imaginary characteristic impedances are very, very rare. Something we won't worry about. So you can do the same thing, that you can essentially get rid of the transmission line and move the load directly up to the generator for purpose of analysis. Because again, there's only going to be an overall phase, and that does not matter. Right? And now, if you think about this, this is common sense. Because the purpose of a cable, a coaxial cable, is just to move the energy from one end to the other end. In many cases, it's because in an experiment you cannot physically put the load directly onto the generator. Otherwise, you just do that. Maybe the device is at the end of inside a cryostat, and instruments are at room temperature. So you have to use something to connect. And we will analyze such scenarios in a lot more detail later on when we look at examples of experimental setups where we are using concepts of microwaves to make measurements, and then how to worry about different aspects of this. Yeah, so you can go through this section, does some calculations on power delivered and things like that. So we move on to lossy transmission lines. And I think we had briefly discussed this in an earlier lecture as well. But the general idea here is that you have, for the most general transmission line, you have inductance per unit length, capacitance per unit length, but you also have these resistance and conductance, which resistance is the one which is in series with the inductor. So just to remind you the elementary section. Just this. L per unit length, R per unit C. So conductance is just 1 over R. So the symbol is still resistance. So whenever you have leakage across the capacitance. And as I mentioned before, it's only the lossless, the low loss line is basically the only practical scenario one could encounter, because having a transmission line which is extremely lossy is in some sense of no use. Having said that, there is a whole part of research in our lab which works on lossy transmission lines. They are used specifically for attenuating signals, and we don't worry too much about the details of the properties of propagation, frequency dispersion, and so on. But when we talk about transmission lines as a means of conveying signals from one end to the other, we don't want the signals to be very lossy. In the case of cryogenic experiments, where the signals have to propagate from a room temperature environment all the way down to the cryogenic environment, there is a different need which requires your transmission lines to be actually crossed. And that is related to the fact that the noise which is present, the thermal noise which is present at room temperature, you don't want it propagating all the way down to low temperature. The second is that the material you can use for such cables also cannot be very good conductor. Now, you know about the Wiedemann-Franz law that thermal conductivity and electrical conductivity go together. So if you want a low loss line, then it has to be made out of a material which is a good conductor of electricity. And consequently, it will also be a good conductor of heat. And that creates a problem in a cryogenic environment, because in order to keep the cryogenic environment cold, you cannot have a thermal load also coming. Just the very fact that there's a piece of wire going from 300 Kelvin down to say 10 millikelvin or 300 millikelvin, or whatever your experimental temperature might be, you can dump thermal. So there are special cases where the losses are actually there and one needs that, but in most cases we will not worry about it. And the simple model of a low loss line basically is that these quantities here are small, especially this one. So R is much small compared to omega L, and G is much smaller compared to omega C. So of course, here omega comes into the picture, which means that these approximations are not valid at very low frequencies. That's why sometimes this is also called a high frequency approximation, because you will never be able to get into this situation at very low frequencies, because at omega equal to 0, this term sort of goes up. But we're also not concerned about very low frequencies when we're talking about microwave engineering, because that's sort of outside. That's the circuit theory. But so when you do that approximation, you can get an expression for this propagation constant, which earlier was purely imaginary and hence gave you no attenuation in the signal. Now it's going to have a real part as well, which is given by alpha, and that basically is proportional to this quantity. So you see that this resistance per unit length gets normalized by again the characteristic. So it's all relative to that number, it tells you how much attenuation. And you make this approximation that the propagation constant is still, the imaginary part is still the same, which means that in terms of its frequency response and the electrical length, speed of light, you don't get any change to first order in these quantities. And this also allows you to approximate that the characteristic impedance itself is also the same as before, which is square root of L over C, and you don't have to worry about the Rn. So the only thing it adds is an extra real term in the propagation constant, right? So where does a real term go in the propagation constant? It goes into this e to the power term. So when you had only a imaginary part, it was e to the I something t. So that just is a phase evolution. That's what happens when the wave propagates. But now you're going to have an e to the power alpha, x here now, not t, just the distance. And that's going to give rise to basically a reduction in amplitude. And that's what you expect from a lossy line. You think that as the signal propagates, its amplitude is going to decrease, or the power it's carrying is going to decrease as it goes from one end to the other. So here they mentioned that this is known as the high frequency low loss transmission. The main point being that the propagation constant and the characteristic impedance can be considered in that of the lossless case. So that doesn't change. I have never come across any application where the idea of this distortionless line has actually been used. But this is again a special case that the thing you worried about in the case of the loss, apart from the fact that there's no loss, is that in general your response as a function of frequency is going to change. In this low loss approximation, we got this result that Z0, Z0 and the propagation constant are as before, so they don't have, there's no change in the velocity of propagation at different frequencies. But in the most general case, that would happen, right? Which means that if you are sending signals which consist of many frequency components, they are all going to propagate at different velocities. And at the end, they're not going to arrive in phase as they were. Right? So which basically means that your signal will get distorted. So this is called frequency dispersion in a line, and it can be an important problem, especially for lossy lines. So depending on how narrow band or broadband your signal is, in going back to one of our discussions about these transients, and when you turn something on, it's not, even if you turn on a pure frequency, the very fact that it turns on at some point means that it has a finite bandwidth of signals. So if you are propagating very, very short pulses of, say, a signal at 5 gigahertz, but let's say the width of that pulse is only a nanosecond or so, then that represents a very broadband signal in frequency space. And the bandwidth will be roughly inversely proportional to the width of this pulse. And if that pulse is traveling through such a line where the velocity is different at different frequencies, then it's not going to reappear at the other end with the same shape. It will actually become distorted because of its different frequency components changing. So there is a special condition if you are able to do this, that given that you have R and G in your line, if you're somehow able to make this condition satisfied, then you get this special result, that basically cancels out the frequency dependence. And again, you just get an attenuating line, but with no frequency dispersion. Now, as I said, I have never come across an example or an application where one could do this. The problem is, how does one do it? Because we think, as you will see a little bit later when we talk about the examples of how these transmission lines are made, you don't have a lot of control over such aspects. And especially wanting to change L per unit length and C per unit length independent of R and G, because that's what you assume that some R and G is given and somehow you're tuning L and C. So they mention here that this is typically done in I guess you can call them artificial transmission lines, that they're actually composed of an array of inductors and capacitors. So you would add extra inductance and extra capacitance to the structure. So the only way to do that is that if you are not able to change the material property, so you have one unit cell which has some inductance, some resistance, some capacitance, some conductance. If somehow you are able to add an extra inductance or extra capacitance to that structure and make your unit cell a new unit cell, then you can tune it. But that method of adding the inductance or capacitor cannot be the same as just extending the unit cell of the same material. So it will have to be some other material. So overall, it will look like a new unit cell which satisfies this particular problem.
Okay, can't we do it time? Pressing it and is there like putting strain and then changing the property? I don't know if such material exists, but
well,
it will be a dynamic something.
It's you're saying that by putting a strain,
Yeah,
you bring it closer, so the capacitance.
Well, yes, yeah.
No, but see that's
no, also like this unit cell will also change, expand, and it might result in some change in the band structure. So
yeah, it might be possible, but there's not much room in a real material. So the only thing you can control is the geometry.
yeah, like a very thin material, we can like not very easy, but the thin material, if it is possible to control the geometry.
So one can control the geometry when you're actually designing the transmission line, but usually
dynamically, like when the system is set.
oh.
That's because
you want some kind of a tunable knob.
Yeah, because if this condition need to set, I don't think it could be done beforehand.
Well, you will. So the only way you can imagine this is that only way I can imagine this is that you are constrained to use some material platform to build your transmission lines, and then you try to do your best, and it's a lossy system, and you try to do your best to make it dispersionless by getting as close to this condition as possible. So it will become a little bit more clear when I show you the different transmission line structures, and then you see what freedom you actually have in constructing.
So also you can repeat your comment about this room temperature going to the low temperature. This is the temperature gradient. So what happened to the noise? We are doing the mission.
So I will discuss this in way more detail in a later lecture, but essentially the point I was trying to make is that if you had a perfectly lossless line going from room temperature to low temperature, then at room temperature, you usually have Johnson noise or Nyquist noise associated with the components at that temperature. And if the line is lossless, then that noise will completely reach your experiment with the same intensity. And that is usually incompatible with the requirement that one of the reasons you often go to low temperatures is that you're actually trying to reduce the noise. So it almost necessitates this fact that any such signal has to go through a bunch of losses, so that by the time it reaches the low temperature, the room temperature noise is actually almost completely eliminated. And you're dominated by the noise which is now corresponding to that temperature and the components which are there. So the Johnson's noise and Nyquist noise. So this is a very technical aspect for cryogenic experiments, and I will be discussing some of these examples in a lot more detail at a later stage. But that's what I meant. There's a side fact that if you have such a lossless line, it will also be a very good thermal conductor, which is incompatible with making sure that the low temperature stage actually remains cold. So, one of the very important requirements of any low temperature system is that, first of all, you find a way to remove heat from it. That's how you reach the low temperature. And then you prevent all mechanisms of heat coming back into the system. But that's why you have a vacuum chamber.
But it's already in a heat path, so isn't like all the heat that can transfer getting absorbed by the heat path.
Yeah, but then you will, so whatever mechanism is causing the heat to be removed, if you're using, say, liquid helium, then you're going to increase the boil-off rate of liquid helium unnecessarily.
Okay.
Or if you're using some other kind of technology, at some point it will not be able to keep up. So usually in this cryogenic system, the lowest temperature is defined by an equilibrium between how quickly you are removing heat and what is the leftover heat influx. So when the two get balanced, you reach that's the temperature at which stop. So now by adding a very good thermal conductor, you're going to make that worse. So it will heat up.
We have a higher temperature.
It will have a higher temperature, which is not going to be acceptable for most situations. Okay, so that's all for this discussion line, discussion this time. So the next topic is about a terminated lossy line. This builds upon the concept we looked at last time, that if you have a load impedance and then you have a sectional transmission line, then how that transmission line transforms that impedance. And that, of course, assumed that the waves which are propagating from one end to the other end, they only accumulated phase, and all the boundary conditions will determine how they will reflect, and that's what led to the transformation effect. So if you have a situation where this line is not lossless anymore, then you have the situation that now not only the phase is changing, the amplitude is also changing. So there are of course some naive effects. So this first part of the section, it basically calculates the power delivered at the in such a system. That is not such an interesting. So the main point I want you to think about here is what it looks like from the point of view of, say, matching to that particular load, in terms of how much attenuation you get. So let's forget that there is dispersion. So we assume that it's a dispersionless line. So all frequencies are propagating at the same. There is some loss, and by making that, by controlling that loss parameter, we can make it larger or smaller. So I'm sort of slightly creating an artificial scenario where I'm allowing the loss to become high, but I'm still maintaining that the dispersion properties are still the same. In practice, how one can do it is a different question. So what I want to ask you is that we draw here. So I have a source which has a source impedance R is equal to Z0. I have a transmission line of characteristic impedance Z0, and I terminate it with an RL not equal to . If I look at this system at this point, and I say that there is some attenuation, so this is a lossy line. What will happen as the loss increases to the reflection coefficient seen at this particular point? Gamma. Yeah. So initially, let's assume that the transmission line is of zero length and zero loss consequently. Then we will have a reflection coefficient which is just given by RL minus Z0 over RL plus Z. So some finite reflection. Now I'm introducing this transmission line, and I'm saying that now I'm going to increase the attenuation of this transmission. What will happen to this gamma as the attenuation becomes very large? Gamma will become close to zero. Okay. Anybody else?
There will be no signal.
Hmm?
There will be no signal.
There will be no signal where?
Like, if the attenuation is increasing, the signal intensity is flat with what it is.
Okay. Any other thoughts? Actually, I learned that your correct way of saying is position. Right? No? Because I saw your Bengali classmates call you Osh.
Yes, sir.
So, okay. So, you are that Bengali.
I think the proper noun should be left.
What will it be?
Discussion coefficient.
Go down. Okay. Right. So, all of them are right. In the limit of very large attenuation, as Panya was saying, that the signal is never going to come back. Okay. And because the source impedance is matched with the impedance, characteristic impedance of the transmission line, the wave will get launched. Okay. There is no reflection at that point in the first instance. But then by the time the wave propagates down the line, it's going to go down to very small amplitude. Of course, depends on the impedance, how much attenuation you have. But the larger the attenuation, the smaller that wave will be, and then it has to come back as well. So at some point, irrespective of what is happening at the end, nothing ever comes back. So when nothing comes back, that's the equivalent to the situation of a matched load, right? And that means gamma will be 0. So there will be no reflection here. Now this seems like a strange example to give, but there are two practical consequences of this when one uses this kind of a scenario, or one should be careful about this kind of scenario. Imagine that your job was to measure the reflection coefficient of some device which is connected here. It could be a resonator or some impedance. So we looked at the reflection coefficient of a resonator in some of the early lectures. What this is telling you is that if you use a one-port setup like this one, so you have a source and it sends some signal, reflects from the device and comes back, you will not learn anything about the actual device if the intervening transmission line is a highly lossy transmission. Again, it seems like an odd scenario, but in most cases, when you look at only reflection measurements, you just connect your device directly to this instrument called a vector network analyzer, which can measure, it will send out a signal and measure what comes back. But if for some reason you have to connect a transmission line between your device and the instrument, you cannot use a highly lossy transmission line at all. You will completely lose the information of what the reflection coefficient. So in the worst scenario is that if the attenuation is so large that you get nothing back. Right? So that's the way to think about it. The information about the reflection coefficient here will never make it back to your instrument here, so you cannot measure it at this point. So this again connects back to the point I made about the cryogenic experiments that you need attenuation. So then, does that mean that you cannot measure reflection coefficients of devices at cryogenic temperatures? No, because you use a different type of a device to divert the outgoing wave, the reflected wave, through a different cable. And this is a device we will discuss later on, but there are actually a few different types. But one of them is called a circulator. Okay, it's a 3-port device. And it has this special property that it only allows microwave signals to propagate in the direction shown by this arrow that comes with the device. So if this is port 1, 2, and 3, what this means is that if you send a signal at 1, it will come out at 2 and not at 3. If you send a signal at 2, it will come out at 3 and not at 1. And if you send a signal at 3, it will come out at 1 and not at 2. Okay, this device is called a circulator. And it actually is a device which uses ferrite components and a magnetic field to achieve this kind of an operation. So this is something we'll discuss towards the end of this course. But I just wanted to introduce this. So how does this help solve this problem? You can now have an input line, which may be very lossy, and then this connects to your device. So a wave comes in, reflects, and then transmits out this direction. And then you can put some amplifiers here to boost the signal, so that even if there is attenuation in your lines because of the cryogenic environment, you can actually recover the information. So here the return signal is not going past the same path. The important point here to note is that the fact that the incoming signal is attenuated is no longer a detrimental thing, because all it does is that it reduces the amplitude of the signal that is incident on your device. You control that. And if you want a certain amount of power to reach your device, you put correspondingly larger power. If your attenuation is say 60 dB, you put the right amount of power at room temperature, so that the correct power is reaching your device. And then the signal is actually going through a different path where you can put amplifiers. The same does not work if the signal is coming back in the same way, right? Because you can't have an amplifier going in the different reverse direction. So this allows you to separate the incoming and outgoing waves. There is another device called a directional coupler which also does that. Yeah.
But how do you, select the omega? Because let's say we have three components in omega. Let's say
How do you, sorry?
select the omega to reach the T with load increase here. Let's say we have three omega in the signal, omega 1, omega 2, omega 3, and you want to reach omega 2 to the field.
Sorry, by omega you mean frequency? Right?
Frequency.
Yeah.
So how do you cut that omega 1 and omega 3?
But I'm not talking about filtering. Why I don't understand the question. Why are you asking about omega 1 versus omega 3?
Because you told that you have the Johnson noise and you want to cut that Johnson noise to reach the source, right?
Oh, but that is across all frequencies. Right. So the attenuation which is going to be present in this part of the line is attenuating all frequencies in the same way. Because the simple model we use of Johnson noise is that it's a white noise. This has the same intensity at all frequencies. So in practice, there are cutoffs and things like that. But this device doesn't do any frequency selection outside of the band of the operation. Now, this was something I was not going to go into now, but this kind of a circulatory device actually only works over a narrow range of frequencies, just like impedance transformers and other things, because this also relies on a resonance condition, and usually they have octave bands. So the one we typically use in our experiments is 4 to 8 gigahertz. So outside of that band, it doesn't do this operation. So if you go away from that band, then the signals will start leaking into the wrong ports as well. And even in the operating band, it's not 100% perfect. So usually we define tolerances. So what it means is that if you send in a signal at port 1, 99% of that will go to port 2 and 1% will go to port 2. So you have to deal with those small errors which come. But there's no filtering going on within the band. Any other question? Yeah.
So instead of using this circulator as well as amplifier, what if we do this thing like you said earlier, we can use multiple transmission lines of different relating to the ZL and Z0.
Yeah.
And then between the transmission lines, we can use multiple amplifiers as well, like transmission line amplifier, so then we won't have to circulate and signal will also not be lost.
So you're talking about using different transmission lines in the context of impedance transformers, or?
Yeah, so maybe what if after the transmission line we can use amplifiers and not circulator? So what if we not use circulator instead of
No,
we
so
just like
okay. There are certain things which are not possible. So for example, if we have a section of the transmission line. And then you say that I want to put an amplifier.
Yeah.
And then I have some another section of transmission line.
If the effective length of like this
And
transmission line is less than the earlier.
And then you have your load. Okay. Several problems with doing this. First is that the Johnson noise you were trying to attenuate, you have now increased it again. And in fact, you made it worse because amplifiers add their own noise as well. So if the input temperature was here was some effective temperature was P1, the output temperature is going to be gain times T1 plus some noise from the amplifier. So that problem has been made worse. Second, when the wave reflects, what happens when it reaches this amplifier? Amplifiers are unidirectional. Most amplifiers are unidirectional. And in fact, this is a property required that it should provide gain in one direction and allow more transmission in the other direction. So the signal is never going to cross the amplifier. So you cannot measure your reflection coefficient at this point. So you need a path where the signal can propagate in both directions to do the same. And that's why if you have a very attenuating line, you cannot.
So when you use circuit as well as amplifier, will that amplifier
That amplifier goes in this line and it only amplifies the signal which is going away from the device, which is coming back to your receiver. The signal which reaches your the actual device whose reflection coefficient you're measuring is still this signal, which has not been affected by the amplifier.
will it also amplify the Johnson's noise?
Yes, it does, but it's now going in the output direction, so you don't care about that.
Okay.
The worry is that this Johnson noise doesn't reach your device yet. Now, we are getting into some technical details because if your job is just to measure the reflection coefficient, it doesn't matter. But usually the devices which you measure at very low temperatures have very sensitive properties which will get disturbed if you have too much noise coming in. So it's to take into account those kind of things where this becomes important. It will become, we will discuss one or two such examples in a lot of details later on, so it will become clear what I mean by that. So those will be like examples of actually using these concepts to make real world measurements. All right. So, right, so you cannot do reflection coefficient measurement with a single path, which is lossy. But the very fact also that you realize that the reflections sort of go away, right? If you have a very lossy system. So sometimes this is used, even though it is not ideal, it is used as a crude way of impedance matching. So if for some reason you're not able to use an impedance transformer, in order to minimize reflections and standing waves, you can actually put a small amount of attenuation in the system. So it's basically like saying if you have a section of transmission line which has some reflection on both ends, the standing waves will get reduced if the line is lost, just because the signal is propagating back and forth and its signals are actually dying down. So that can sometimes give you a crude way of reducing reflections in a real setup. So there will be some homework problems on this, which I hope to give the first assignment by end of this week, where you will play around with some of these ideas with loss of transmission. All right. So we then move to thinking about transients on transmission. We've sort of discussed this in the context of signals turning on and off. But there are some examples here which give you a nice picture of how to think about what's happening. And now we're going to think in time domain. So remember we had introduced this idea that if you have a finite length of transmission line, then till that wave and you're at the input and there is some source and you turn it on. And even though the other end could be a short circuit or an open circuit that the wave is going to reflect, till that enough time has passed that the signal can actually propagate all the way to the end and come back, your source is not going to know that the other end is actually a short circuit or an open circuit. Right? Because all of these effective input impedance and everything we have discussed is a steady state picture. Locally in time, it only sees a transmission line with a characteristic impedance C0, which means there will be no reflected wave created at that instant of time. So here's some examples of how to think about this. So what is this scenario? You have a DC voltage source here. So this is just some fixed voltage. It has a source impedance Z0, DC, and it is connected to a finite length of transmission line of characteristic impedance Z0. And there's a switch here. So initially, this source is not connected to the transmission line. And at the end of the transmission line, it has Z0. So the situation we are going to analyze is what happens when you turn this switch on and connect the DC source to the transmission line. Now, we will actually do this problem in the reverse order than how it's explained here, which is in steady state, how much voltage is going to be dropped here? So your DC voltage is V0. What is the voltage that's going to be dropped across this? Remember, this is a DC circuit.
What is that also? That impedance of the transformer
Is Z0.
that is for this.
Yes and no, but you're thinking in the right direction. What is the role of the transmission line at DC?
It is just a resistor, I think.
It's just electrical length becomes zero.
Electrical length becomes zero. You are saying it becomes a resistor of value Z0. Anybody else? Are you talking about only the transmission line or everything else? So let me be more explicit. So I have this transmission line. I just have this transmission line of characteristic impedance Z0. DC current won't flow. No, Z0 is real. Z0 is real. But what is the property of this transmission line at DC?
If electrical length is zero, it doesn't make any sense. It's just like I even say. It's just Z0 in the ground. Z0 is the source.
So it is earlier the AWR also. Right? So the zero was not being removed.
That's one way of thinking about it, I guess, that because omega is zero, effectively the electrical length is zero. Because the thing is, you cannot really define electrical length for a DC signal. Then what does the physical length mean? It's zero for all physical lengths, right? Because the time available to you is infinite, because it's 1 over omega. So a transmission line at DC is just 2 wires with zero resistance. So zero resistance in what sense? Zero resistance between these 2 terminals. Between these 2 terminals, it's zero resistance. Between these 2 terminals, it's also zero. So these are all assuming to be perfectly conducting wires. And there is infinite resistance between the 2 terminals. Okay, so this actually goes back to the simple picture of low frequency circuits, that you have a DC source, a Z0 source load, then this is just a wire. And then you have Z0 as the load as well. So then in that case, what is the, it's just V naught over 2, right? Just divide by 2. So now we will see how you can get the same result, but by looking at what happens in time domain. Right? Why you are thinking of it? Because when you first close the switch, you have actually created a situation where you have started the voltage at this point. At this point, the voltage was 0 and then it became some value. Okay. So the question is now, when you turn the signal, the switch on, what is the voltage at this point exactly at that time?
So then we just switch on. We don't know that there is some Z naught there. No.
Initially, it should be, not over,
V naught over 3.
because, initially it will be great, but when I start the switch, it will see some high frequency. And then the effective is, sorry, then the impedance matching will be satisfied there. So initially, it will be not.
Okay, V naught. Any other options?
We can think of
Yeah.
this DC being switched on as going from 0 to 1 some parity.
So we are not worried about the the fact that you cannot have an instantaneous voltage, but let's say the voltage turns on instantly. See, this voltage is always on. This part is always on. What we have done is we have connected this switch. Let's say that the switch is some idealized thing, closes immediately and gives perfect contact. At that point in time, so see, just before that time, the voltage across these 2 points was 0. So I'm asking, what is the voltage immediately after closing this? Yeah.
When closing the switch, the voltage drop after the Z naught will appear at that point. That will be,
Equal to
E naught.
this voltage.
Yeah. That voltage will drop after that resistor, then that is after.
Let me add now that it's a trick question.
Since it's not AC, I'm not convinced that it will take it.
Huh?
I don't think it will take any time since it's not AC.
What will not take time?
But we not going to agree with it. Like, there is nothing to travel. And there's no switch time.
Okay. Most of your sentences are correct except one very key statement. Is it DC?
If it instantaneous, then it's
Really? What happens when a voltage suddenly changes from one value to another value? We call that a DC signal. It's not a DC signal. In fact, it's a signal with almost infinite bandwidth going all the way from DC because it's an instant. I'm saying that it's an instantaneous rise. So you'll have Fourier components all the way to becoming smaller and smaller. So the moment you look at the picture of the transient, you go back to your standard AC picture, right? The important point is that it's a dispersionless line, so all frequencies, everything is traveling in the same speed. So what is the voltage that will appear at that point? Is it V naught? Is it V naught over 2? Is it V naught over 3? I don't know. How did you arrive at 1 over 3? Like, what was your?
So this is, I was thinking of like a series based on future.
So again, this is a very sort of an artificial example, but there are a few key concepts I want to burn into your memory again, because I can see that some of the things I've mentioned before, because of low frequency instinct, you're saying those wrong things again. A transmission line has no meaning of a resistance along the length of the transmission line, right? In the ideal case, in a real transmission line, there will be a resistance, but we are not talking about that. What matters is how voltage drops happen across the two terminals of the transmission line. So remember, we have actually analyzed this situation in a different way where we did not say that this was an AC signal, sorry, a DC signal. Let me, if let's say that this V naught, instead of being a DC signal, was actually a sinusoidal signal, something at omega, frequency omega. So when the switch is turned on, then it's like saying that I had something and then I got some voltage like this. So if the initial amplitude here was A, what is this amplitude at this point? How will you calculate that? Given all the information which is here. Let me add a hint. It actually does not depend on the value of this. I'm just asking what is the voltage at this point. I've changed the problem from being a DC signal to an AC signal just to motivate you to think in the right direction. And I'm saying that the answer actually doesn't depend on what is connected at the end. At time t equal to 0. It's the same idea that the wave has not had a chance to reach the end to even know that it exists. So it doesn't matter what is connected. So if you have a source with characteristic impedance Z0 launching a wave into a transmission line of characteristic impedance Z0, what is the voltage that's going to show up here at that instant? Yeah.
V naught minus V jet by
V0
minus V jet by jet.
what is VZ?
VZT, small t.
Oh, no. So this VZ is just saying that that is what the voltage across at any point in this line is. So this is V equal to 0. So what I'm asking you is what does V of 0 as a function of t look like?
So it should be
Should be
Not right.
exactly. It's V0 by 2 because at AC frequencies, the transmission line of characteristic impedance Z0 looks like a resistor, shunt resistor of value Z0. Because you have not seen any of the, in fact, that is the meaning of the characteristic impedance. It tells you locally at that location how the voltages and currents are going to be related, and that relationship is Z0, right? The V over I at that location is Z0. So the reason this is tricky is that we started with the DC source, we looked at the steady state picture, we realized that that transmission line has no role to play. But then when I turn to the picture of a transient, when you turn the switch on, it's no longer a DC picture, but it has to become a DC picture eventually, right? That's the steady state. We have not reached steady state yet. So the initial wave, which is launched, is also going to look like this at that particular point, z equal to 0, and its amplitude will be V0 over 2. Then that V0 over 2 pulse is going to travel along this transmission line, right? So at a later point, so each of these points at a later point in time will reach V0 over 2. Yeah.
Like,
Which part?
so you're saying that when it's just for the AC part.
No. So we are now, what I'm saying is that it doesn't matter whether it's AC or or a DC signal.
Any signal is saying when it just starts,
Yeah,
it just saves the transmission line as a resistor for of zero, and then ground is.
yeah. So across here, so it looks like this between these two terminals.
So basically, till wherever the signal is been able to, reach at that point, it just saves that.
Well, so you only have to worry about the boundaries, right? Because once the wave is launched, which means you have defined E plus at that particular location, then the transmission line's job is just to propagate that along it. So the thing to think about is that what happens at this particular point. So if this transmission line had a different characteristic impedance than Z0, then it will be the corresponding ratio. So it will be whatever Z0 over Z0 or Z0 bar. So at t equal to 0, this point here will see a voltage which is V0 over 2. And at subsequent times, and at that same time, somewhere else, the voltage is still 0, right? So as time proceeds, this voltage will keep becoming V0 over 2 along this line all the way to this point. So at some point later, a later point in the transmission line will reach V0 over 2. So if you are able to plot the voltage versus time at different locations, so this was now Z, sorry, not Z, this is T. So this will be at Z equal to 0, then a little later point will look like this, a little later point will look like that.
T is actually the length.
So T is the x-axis, and the different curves correspond to different Z's along the transmission line going from left to right. And then at the time, which is basically this length L divided by the speed of propagation, that wave will reach Z0. Okay. What will happen at that point?
Transmission line will be like something.
Okay. Because the transmission line is now matched to this Z0, there is no reflection. So there is no further division, because remember that initially also there was only a right propagating wave which was created, and then that basically terminates at this point. So the total voltage at that point is usually the right plus the left propagating wave. But since there is no left propagating wave, the amplitude V0 by 2 will appear exactly at the on the resistor. So you get V0 by 2. And then that's where the transient picture ends. Right. No further reflection. Now, what is the steady state picture? The steady state picture is that the voltage on the resistor, the load resistor, is V0 by 2. Which is what we had calculated before. So the transient picture basically tells you that this pulse travels, this kind of a pulse here, travels from that edge all the way along the transmission line, reaches the other end, then that's the end of the transient picture. It has reached the steady state, which is what we got from the DC picture. Is that part clear? Slightly more complicated version of this is this. When you have a short circuit at this end, what's the steady state voltage at this point? Same, everything is the same. The only thing we have changed now is the that the load is now a short, zero impedance. So steady state voltage at this point is
16, we know.
V0 by 2. Any other answer? Steady state picture, steady state voltage at this point,
Steady state, that's the same as.
V0, V0 by 2, V0. Any other answers?
I just think to do.
Zero. Yeah. It's a short, right? The impedance between these 2 points is zero, so there is no voltage drop across. So how does one get to that zero answer? That's what's shown here. Now, again at time t equal to 0, the wave which is launched on this transmission line is still going to have the same amplitude V0 by 2, right? Because it doesn't depend on what's on the other end. What's going to change is that the steady state picture does not end till you reach this, like after you have reached this point. But now, at this point, you have reflection coefficient of 1, sorry, -1, because it's short, right? So gamma short is -1, and gamma of open is +1. Because it's Z minus ZL over Z plus ZL. So ZL is 0, or so the other way around, ZL minus 0. So ZL is 0, -1. So you now have a wave which is exactly the opposite sign. So at that point, the voltage will also go to 0, because V plus plus V minus will be 0. So that's the total voltage. So the total voltage here also has to be 0. In fact, that is the boundary condition, right? But in order to satisfy that, you have a forward going wave coming with amplitude V0 by 2. It has to set up a backward going wave of the same and opposite magnitude, so that the sum of those two add up to 0 at that point. And then this, initially remember the incoming part set up a voltage V0 over 2 slowly across the line. And then it became 0 here, and then that reflected wave will cancel that forward going wave and make it 0 all along the line till it reaches back to this point. And what happens at this point? You are again have a matched situation, because you are propagating from Z0 transmission line to a Z0 load, right? So this is something I get specifically mentioned, but the source itself is this is an ideal. This is what's called the Thevenin model, right? It has 0 impedance by itself, so you don't worry about it. So when the signals are reaching the source, what matters is what is the impedance from this point to ground, and that is the same as Z0. So this is a strange situation where you started with a V0 by 2 wave. It had to go all the way to realize that there is a short circuit there, and then come back and then sort of cancel that out and give you 0 at this point. So as a function of time, you see things going up to V0 and then coming back to 0. And then the third picture is that of the open case.
There should be.
So again, initial part is the same, but now the steady state picture, of course, is that if I now measure a voltage here, it's going to be V0 because there is no load. So you're measuring the open circuit voltage. And the way the V0 gets stepped up is now you have V0 by 2 at time t equal to 0. That will propagate. Now the gamma is +1. So the returning wave will actually be also V0 by 2. And then the 2 will come here, add up to give you V0. It sounds like a very silly problem, but it really allows you to carefully think about transmission line concepts, steady state picture, and what happens as a function of time when you think about transients.
So this basically, whenever we think of circuits, we always think in the sense of, in the complete sense. Like we can never think like if there is something there and the current is not there, we cannot calculate individual voltage drops ever. But here, in some sense, we get another picture altogether where it is slowly building up.
Yeah, there are basically
Fields.
two things you have to keep in mind, that when we talk about low frequency circuits, there's no concept of time causal effects, like something happened and then something later. Even though in a real circuit there are delays because circuits takes time to respond. But we always think about the steady state picture straight away, because that's over the typical time scale, the time scale it takes for the steady state to happen. Remember here that this, even though we looked at this entire process, all of this is going to happen at speed of light. Your human brain is not going to be able to sense this, but you can. I will actually do a demonstration of this using oscilloscopes and a section of a long transmission line. You can see this happen, and then a nanosecond time scale is trivial for modern day instruments to capture dynamics, right? So we can actually see these voltages being set up and then turning back on, or being set up and then enhancing. Right? So it's trivial to actually see this. Speed of light is not that large because we can look at nanosecond and picosecond time scales very easily these days. So I will do that demo maybe in the next class. Okay. So one last thing to think about. If I have a transmission line of C0, and then I connect it to two transmission lines like this. Okay, so they are actually connected in parallel. So there's an incoming line, and then there are two lines which are going away from it. And they are both Z0. And I have some incoming wave coming in with, say, some amplitude V0. What will happen at this junction?
Like these lines are terminated.
There's not. I'm not worried about what is happening. I just want to know what happens when this pulse or this wave first reaches this one. So remember, this is what we discussed, that if you're only interested in the local and time, we don't care about what's at the.
It's basically C0, series C0 and then to parallel.
Okay. Will there be a reflection or not?
Like, will they go straight from Z0, right?
Why?
Parallel.
Because they are in parallel. Exactly. So you have incoming is Z0, and at that point, the combined impedance of these two transmission lines is actually Z0 by 2 because they are in parallel. Right? So that means there is an impedance mismatch there. So you're going to get reflection. Yeah, brother. Yeah. Are you in the office? You're coming there? Okay. I'll see you there in 5 minutes. Clean room alarm has gone off. Yes. How many of you have Airtel connection here? So, have you guys been noticing problems in dialing landline numbers from your phone? Huh? Half the time it doesn't connect or do some errors. Okay. There was a alarm from the keyboard. Can you just make some calls? I'm not able to make calls from my phone. I'm just wrapping up a class. But I got that they contact Santosh or Vedanta or something. So, so the reason for this example is that there is this component. Some of you have worked with PLC cables and things like that. There's this thing called a T junction. You use that to send signals to multiple places. Depending on what you're doing, it can be a very bad idea. Because you are exactly doing this configuration. You're connecting two 50 ohm lines to one 50 ohm line. You're going to get reflections at those points. If you're working with low frequencies and not like fast transients, then it's okay. Everything will be very stable. But if you're working with high frequency signals, even like hundreds of megahertz, you will see this affect your voltages you might get. And if your loads are also 50 ohms, you actually see the voltage will be half of what you have used. So this is something to again keep in mind, that splitting signals at microwave frequencies by just taking wires in multiple directions is in general a bad idea. There's a proper way of doing that. We'll see that later in the lectures when we talk about how to split